This is a re-record of this section on spherical mirrors. I just added a few different examples so you could see the calculations. Spherical mirrors, basically concave and convex mirrors, produce a slightly different image than what we get with a plane mirror, because we're going to actually change the magnification. And especially with the concave mirror, we have the possibility of a real image, which for the plane mirror, we only had the virtual image. So in defining spherical mirrors, obviously spherical mirrors are mirrors with a spherically shaped surface. The radius of curvature is basically defining how much the rays are either going to converge or diverge, depending on if it's a concave or a convex mirror. The radius of curvature, if it's stronger, then obviously it's going to be a more divergent or convergent type mirror. If the radius is larger, it becomes less of that. And if we take the radius to infinity, we actually get our plane mirror. So again, we're taking a spherical surface or some part of a spherical surface. We're coating it. If we're coating the inside of the spherical surface, it's concave. And if we're coating the outside of a spherical surface, it's convex. And again, concave versus convex, the way I like to remember it is concave sort of caves in, if you want to remember it that way. Convex bows out. And the concave mirror is actually the more important of the two, because the concave mirror is the basis for a reflector telescope. Now, we do have limitations with a spherical surface. It's not the ideal surface. We make the spherical surface because it's the easiest to grind. It's the easiest to make of all the different surfaces. And therefore, it is the one that we look at here. However, the correct shape for a mirror to avoid what's known as spherical aberration would actually be a parabolic or a hyperbolic shape. Those are difficult to grind, and therefore, oftentimes with lower quality optical systems, we opt for the spherical shape. The spherical shape. Now, in defining how the mirror operates, one thing that's going to be very, very important is something called the focus. The focus is basically the place where, if we have an incident ray, and this incident ray is coming parallel to the mirror, the incident ray will converge or reflect back into the focus. So here we can clearly see we have this incident ray right here. It is going to reflect at some angle such that it takes it through the focus, and the focus is going to be half the distance of the center of curvature. And the reason for that is, if I take a line normal to the surface to the center of curvature, okay, that essentially being a normal line, if I define the angle of the two rays, incident versus reflected, our angle of incidence has to equal the angle of reflection for the law of reflection. So again, a line going from the center of curvature to the surface of the mirror, okay, from C to X here, is going to represent the normal to that reflecting surface. So again, an incident ray is going to be reflected at the same angle it came in with respect to that yellow line, and therefore go through the focus. And you can do that for just about anything. If I have a ray right down here, again, if I draw my normal goes from C, the point that that ray hits, and as we are required, we must reflect at the same angle that we came in. So there, my green ray would pass through the focus too. So the focus is the point at which parallel rays will converge. Concave mirrors are a convergent type mirror. And the focus is going to be a distance of 1/2 the radius of curvature. Now again, spherical mirrors are not the ideal shape. They do get spherical aberration. And the reason for that is the outermost part of the mirror's surface is actually too curved. And what that does is it focuses the light closer to the mirror than it would otherwise do. And that creates a focus that's not well defined. It's actually spread out. And the spherical aberration leads to a less than perfect type of image. So again, parabolic would be the shape that we would like. Spherical mirrors are just a lot easier to produce, to grind. And if we have a very large radius, it tends to be that the spherical aberration is not as much of an issue. So let's talk about the magnification of a mirror. The magnification of a mirror is defined the same way that we define it for a plane mirror. Magnification is equal to the height of the image divided by the height of the object. This is a lateral height. This is also by geometry equal to the negative of the distance, the image distance divided by the object distance. So that is going to be common throughout all of our optical systems, the plane mirror, the spherical mirrors, and the spherical lenses when we get to that. Now, we can use this equation right here to describe the relationship between the distance to the image, the distance to the object, and the radius of the mirror. That's not the most convenient way to write out what's known as the mirror equation. It's more convenient to actually replace R with F. F is the focal length. F is the distance that the focus is from the mirror. And that would change the equation to, I'll get that to a second. We'll go back here to this right here. And again, this mirror equation is also going to be the same equation that we use for the lenses. So let's go back and look at, again, a bunch of parallel rays coming in and the position of the focus, the position of the center of curvature. And what we can see here is this is the center of curvature, C, and this is the focus right here. And clearly the parallel rays are all converging at that point, F right there. So we would define the distance between F and the mirror as our focal length. Okay, let's take a look at how we can draw a ray diagram for this. For a concave mirror, there are actually 4 different rays that we can construct. And a ray diagram is an approximation, okay? It approximates the path perpendicular to the wave fronts, the path that the light is going to propagate, or the wave fronts are going to move, are represented by these rays. So here we see one ray up here, shown in blue, second ray shown in red, third ray shown in purple, and a fourth ray shown in green. How do we get these? Well, let's look at the first ray. The first ray starts out parallel, and once it reflects off the surface, it has to pass through the focus, okay? That's basically just the law of reflection. The angle of incidence has to be equal to the angle of reflection. And again, the reason why this is passing through the focus is because the normal direction is actually a line between the center of curvature and the mirror. Okay, so the angle of reflection has to be equal to the angle of incidence, and that's satisfied by taking any parallel ray and passing it through the focus. All right. The next ray, the red, will pass through the focus first and then become parallel. Now, in drawing this ray, we're basically reversing what we did with the blue ray, okay? Now we're taking a ray from the top of our object. It is going to pass through the focus. And again, by geometry, if I draw a line between our center of curvature and the surface of the mirror, we can see that the angle of reflection is equal to the angle of incidence. All right, so again, in drawing these images, we typically take the top of the object, and here you can see the object is right here. Start your ray there, send it toward the mirror, and then where it intersects is going to be the place of your image. Third ray, if you have the center of curvature, again, that's just twice the distance of the focus. This is the normal direction. So any ray headed toward the mirror that way is just going to be reflected in the same direction. Okay, so that particular ray, I know it shows an arrow pointing toward the mirror, but in actuality, the ray continues back and makes its way back to the image over that same path, just reversed. The final ray goes to the optical axis. And again, we're just using the law of reflection. Here we see that the angle of incidence equals the angle of reflection. A line between C along the vertical axis, along the optical axis, clearly shows the angle of incidence equals the angle of reflection. Now, again, this ray method is very convenient because it shows us where the image is going to form. And here's our object. Again, all my rays are going from the top of that object, and I'm trying to locate the top of the image because the image, okay, the image right there is going to form at the place where all the rays intersect. And to be clear here, we are not really looking at the entire object here. We were just looking at the very top of the object to locate the top of the image. But, you know, once we have the top of the image, we can draw the rest of it. Okay? So that's our ray diagram. Again, when we're locating an image, we can do it one of two different ways. In the previous case, we did it using a ray diagram. Okay? We can also determine the location of the image by using the mirror equation. Once again, it's 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. So let's do an example here. We'll use this spherical mirror, spherical concave mirror. We're going to use the same focal length for the different examples that we have. We have a radius of curvature of 20 centimeters. We divide that by 2, we get the focal length, it's 10 centimeters. And we'll use this to determine the position of an image for different object distances. Okay? Now, it's important to note that as the radius of curvature goes up, it increases, the actual ability of the mirror to converge these rays becomes less and less. So a more powerful mirror would be one with a smaller radius of curvature. And when we're talking about power, we're not talking about the power to magnify. That's something that's very, very different. we're talking about the power to change the direction of the rays, I guess, converge the rays into an image or into a point. So let's take the case where our object distance is far beyond the radius of curvature and far beyond the focal point. Okay, just to explain what this image is. We have my attempt to draw a mirror that's supposed to be a reflective mirror. And here we see the object in front of the mirror and then the image inside the mirror. Okay, we can imagine that our optical axis is passing through the mirror and toward the other side of the mirror. But in any case, we see an image form. And what we notice about this image is, first of all, it's upside down. It's also on the same side as the rays of light. So the light actually is on this side. So we would say that this image is real because all the light is on the same side where the image is. If I were to put a screen here, I could actually project that image onto the screen. You would physically see that image if there was enough light coming from the object. Okay, so it's inverted. It's a smaller size. So we would say that the magnification here is negative because it's upside down, but it's also a magnification. The absolute value of the magnification is less than 1. And again, you can see the 4 different lines that I've used to create the image. Here's the first one, second one, third one, and fourth one. Maybe not in that order. But you only need 2, by the way. You only need 2. If I did the blue line and the, let's say the green line, because the green line's one of the easier rays to do. I just take that intersection. Where the 2 intersect, that would have been the top of the arrow. But with 4, I'm able to confirm that indeed that's the position of the image. So we've already determined, given a radius of curvature of 20 centimeters, that our focal length is 10 centimeters. I'm now going to use the mirror equation, this equation right here, to locate the distance of the image. And what we're going to do is we're going to basically solve for DI. So I'm going to put DI on the left-hand side of the equation and everything else on the right-hand side of the equation. And just showing you 1 over F is right here. We move the distance to the object over here and take that difference. I get an answer that's in inverse centimeters for 1 over DI. I invert that. DI becomes 12 centimeters. And that seems to match what I have here. The focal length, again, 10 centimeters. Okay. And it looks like, yeah, I'm about 2 centimeters beyond the focal length. So that image does work right there. And now the magnification is negative DI over D0. We take all the distances, all the image distances that are positive over here. If the image formed on the other side, we would have taken that DI to be negative. And clearly we can see that our magnification is negative 1/4, which means that it's upside down, it's inverted, and it's 1/4 the size of the object. Okay. Now let's do an object that is still greater than C, but we're moving it closer to the mirror. And we've noticed in our ray diagram that the image has gotten slightly bigger. Not only has the image become bigger, it's moving away from the mirror, and that's what we would expect for a greater magnification. Still inverted, okay? So when I look at this, the object is still smaller than the image that I see within the mirror, okay? And Once again, I use the same exact equation. The primary difference here is that I've moved the object closer. It's now 30 centimeters. That gives me an image distance of 15 centimeters. And, 15 divided by 30 is 1/2. Negative, once again, it's upside down. Moving it closer. What if I move it to the location of C? This is the case where we actually get an image which is just as big as the object, but we would say the magnification is -1 because it's upside down. It's inverted. Okay. So focal length, 10 centimeters. The distance to the object is 20 centimeters. Remember, the radius of curvature is twice the focal length. And by plugging in a DO of 20 centimeters, we get a DI of 20 centimeters also. Remember, it's 1/10 for 1 over the focal length minus 1/20th for 1 over the distance to the object. 1/10 minus 1/20th is equal to 1/20th. We take the inverse of that, we get 20 centimeters. And again, the magnification, -1, upside down, but the same size as the object. Now we're going to move it between the center of curvature and the focal point. Now the rays become a little bit more difficult to draw. You've got to be a little bit careful here. The one that goes through the center of curvature simply passes right through here. Our mirror is actually not big enough in this diagram to have that ray hit it. Okay. Again, here's our parallel to focus ray. Here is our focus parallel ray. And then finally, reflecting off of the optical axis, we get this green ray here. Okay? Now, notice what's happened. As I move the object closer and closer, this is the object. Okay? This is the object right here. That's the object. I'm using the wrong tool here, but this is the object. The image is now bigger. It's still inverted, but it's now bigger. In all these cases, it's also still real. The image is sitting on the side of the mirror where the light is passing. When we do our calculations, we've moved our image. Sorry, we've moved the object to 15 centimeters. That gives me an image distance of 30 centimeters. And because the image distance is now twice the object distance, we get a magnification still upside down, still -2, still negative. Okay, what happens when I place the object at the focal point? Well, if I do my calculation here, I get something very, very interesting. I have 1 over 10 centimeters. That is 1 over the distance to the focal point, okay, minus 1 over the distance to the object. That gives me 0. Now, if you look at 1 over 0, you say, well, that's an undefined number. But if you take the limit of that, it's actually equal to infinity. And the infinity actually makes sense for this particular case because the rays will never converge. Okay, remember, we're looking for the point at which all the rays converge. And if I follow this correctly, the ray that passes through the center of curvature, okay, simply reflects back, hits the mirror, and then it reflects back the center of curvature. Okay. here is the ray. Let me use a different color. Here's the ray that starts out parallel, then it passes through the focus. Here's the ray that is going to go through the optical axis. And notice I don't have a parallel ray that comes in and then passes through the focus. That's not the possibility here. I should say I don't have a ray that goes through the focus and then becomes parallel, because that's the exact same as the blue line that I have right here. But parallel lines, no matter how far you go, will never intersect. Okay, it's actually one of the tests for parallel lines. So no matter how far I travel, I will never come to an image, because the image is at an infinite distance. So no image here. No image here. If you had placed an object there, you would never form an image. You'd never see anything. But if I go in front of the focal point, something interesting happens. Well, two interesting things happen. The first thing is the image is imaginary. Why? Because when I trace the rays here, they converge beyond the mirror where the light doesn't actually pass. So again, let's do our little test right here. We're going to start out parallel, and then we're going to pass through the focal point. And if I trace this back in time, that goes right there. We'll do the one reflecting off of the optical axis. Okay, that goes this way. Again, we trace it back in time. They converge to a point on the opposite side of the mirror. Okay. The image is right side up. It's imaginary. And in this case, it's actually magnified. So let's do the calculation for this and see what the numbers that we get. Again, remember, when the distance to the image is positive, okay, it's going to be on the left-hand side of the mirror in this particular case, because that's where the light is. If the distance is negative, it's going to be on the right-hand side, because again, here's where the actual light is. There's nothing here, okay? Nothing that happens over here has any influence on what's going on. This is really just the virtual realm. So focus still 10 centimeters. Our image distance is now 6 centimeters. 1/10 minus 1/6 is negative 0.067 inverse centimeters. And that gives me my image distance of negative 15. Negative 15 divided by 10 tells me negative sign's gone. Tells me two things. The image is virtual, and it's on the right-hand side of the mirror here. And it's magnified. So that's how you would do these types of problems with a concave mirror, where we have our center of curvature, C, which has a radius of curvature, R. The focal length is 1/2 the radius of curvature. And again, it's interesting to see, because the plane mirror, everything was virtual. We always had a virtual image. It was right side up, and it was the same absolute magnification as the object. But here we have the possibility of a real image. And again, all of these previous cases, the image could have been projected onto a screen. And then the last case, if we go in front of the focus, flip sides, the image now becomes virtual. And we can see that here, okay? We can see the two different cases. The first case on the left, this is probably where the distance to the object is equal to the center of curvature. And in this case, we have a distance to the object which is less than the focal length. And again, real and inverted, virtual and upright. Convex mirrors only produce virtual images from an object. There are the cases where we can use it to create a second image from an image. In that case, you can create a real one, but for the simple case where we're looking at an object's reflection off of the convex mirror, it's always going to be virtual, much like the flat mirror. These are called diverging mirrors because the rays which are reflected off of them diverge. And if we would trace the parallel rays back into space, we would see that the focal point is on the imaginary side, the virtual side. Okay, so here we would say that the focal length is negative, it's less than 0. So, proper convention, once again, if you have a concave mirror, the focal length is going to be positive. If you have a convex mirror, the focal length is going to be negative. And again, we're just taking spherical surface, and we're taking the outer surface, so the center of curvature is within the mirror itself. So the focal point is within the mirror itself. We're on the virtual side. So how do we do a ray diagram for a convex mirror? Well, usually we're going to only be able to draw 3 different rays here, but we're going to use the same thing that we did before. We're going to take one of the rays. We're going to start out parallel, okay? And here's where it becomes tricky. We are going to pass through the focus after the reflection. All parallel rays do that. But we're going to do this backwards. We're going to extend that line to that point in the mirror and work backwards there. Okay, we're still satisfying the law of reflection, because with the law of reflection, the angle of incidence has to be equal to the angle of reflection. Okay, so that would be, the yellow would represent the normal direction here. Notice for, I'll use red here because I don't have purple. Notice for the purple ray, we send it through the center of curvature, but remember the center of curvature is on the other side. So that ray would look like that. And the green ray represents the reflection off the point, which intersects the optical axis, and that goes this way. So again, where those 3 rays intersect is on the virtual side of the mirror. So again, that is not a real image. We can see that also the image has a smaller magnification, and that will always be the case with our convex mirror. A convex mirror, although it's not as important as a concave mirror being the basis for the reflective telescope, it allows us to reduce the field of view. You shrink everything down, you reduce the magnification so you can fit more on the reflection. Seems sort of counterintuitive, but what you're doing is you're reducing the magnification, so what you can see becomes more. Okay, if everything's smaller, you can fit more onto the reflection that you see in these mirrors. So again, we'll use the same radius of curvature. We're going to use -10 centimeters. Before, our concave mirror was 10 centimeters, so we're just flipping to the opposite side of that radius of curvature. We place the image at 20 centimeters. This gives me an image. We place the object at 20 centimeters. It gives me an image distance of -6.7 centimeters. Again, the negative indicates that I'm on the other side. Okay, I'm on the virtual side. And finally, the magnification is 0.67. You'll always get less than 1 here. And once again, you can't project this onto a screen. this image is virtual. You can see it. Okay, you can actually see this image, but you can't actually project it onto something. Now, here are two applications. In the first case, it's used for security. You're able to see more of whatever you're trying to watch. In this case, it's a convenience store, and it's a very inexpensive way of seeing things that you wouldn't be able to see with a plane mirror, because a plane mirror would be reflecting a much smaller field of view. You're reducing the size of everything, so your field of view becomes bigger. And most importantly, for this side view mirror of a car, that allows us to expand our field of view to see blind spots that we otherwise wouldn't be able to see. You've seen this before. Objects in the mirror are closer than they appear. Why are they closer than they appear? Because the image created, the distance to the image, is less than the distance of the object. However, we're able to see more here. Like, for instance, a flat mirror would only maybe see this much of this, and we would miss our blind spot over here. But by reducing the magnification, we're able to see to the side of the car we wouldn't be able to see otherwise. This is some drawings that were done by Escher, very famous artist. And the sketches that he did here were, here's a self-portrait on the left. He's holding up a reflective sphere. I think he's actually holding up, this appears to be a silvered glass bottle. Probably holding up the same backside of the bottle. Is probably looking at this side right here, and sketching himself as he would appear. He was excellent in coming up with optical illusions, but also drawing different lines of perspective. And in the second case, you can see again a self-portrait, now with the bottle lying down, showing the different reflections. So very interesting study for a spherical surface, or a nearly spherical surface. Again, just to get everything correct, when the object is in front of the mirror, we say that its distance is positive. How could you have a distance that is negative if it's in back of the mirror? Well, that would be the case where we have an image produced from another optical system, and then that is then creating a second image from the mirror. The image location, if it's real, it's in front of the mirror. If it's virtual, it's in back of the mirror. Focal length, that would be positive for a concave mirror and negative for a convex mirror. And again, to do the ray diagram, you have to remember how the rays reflect. Okay? Parallel before the mirror, then passing through the focal point. Passing through the focal point before the mirror, and then parallel. A reflection along the optic axis. Okay? And then the last one passing through the center curvature. When an object is real, it'll be upside down, it'll be inverted. When an object is virtual, it will be right side up. Now again, the concave mirror is probably the more important of the two, because it was Sir Isaac Newton who first recognized that it was easier to produce a large reflective surface than it was to produce a large refractive lens. So he was able to create the first reflective telescope, which became the basis for all telescopes today. Hubble Observatory has a large 1.2 meter reflective telescope. And of course, that was ground to the wrong shape. So it actually had some aberrations to it that had to be corrected with internal lenses. Keck telescope was one of the largest telescopes in the world. It's been surpassed since by the telescope on the Canary Islands. And of course, the Webb Space Telescope, recently launched, is probably the most impressive of all the space telescopes, with a massive 6.5 meter reflective surface. Now, this is smaller than the Keck telescope, but because we don't have to see through the atmosphere, the images are actually better. And it's designed to operate in the infrared. Okay, that's why they coated the surface of the mirrors with gold, because gold reflects better in the infrared than, say, aluminum does. So that is basically the convex and concave mirrors. And again, concave mirrors, very, very important because they are the basis for reflector telescopes.